This is a dramatic reading of Deriving the Hypercomplex Gravity Field Equations, 4 out of 5, in a little mini-series involving lots of work with field equations. Blogs available by the Stand-Up Physicist, available at science2.0.com. Natural philosophers first searched for a link between gravity and EM before the War of Independence in 1776 in a peaceful scientific discussion between the two sides. Benjamin Franklin had gotten on a sailboat because that was the only way to get to London. He talked about his experiments with electricity with Joseph Priestley. Ben had noticed that there was no electric field inside of a conducting cup. You could put charge in the outside, no electric field on the inside. Well, Priestley knew a similar thing happened inside a hollow sphere of mass. So Joe jumped to the conclusion that both fundamental forces were governed by the same inverse square type of law. So here is actually how you write the fields classically for gravity and electromagnetism. And you go, oh my goodness, that's really very, very similar. You know, it's really kind of passé to be impressed with those relations. You know, we've moved beyond them. But, you know, I was so impressed that I actually got this shirt with the equations monogrammed on the cuffs, because it's much easier to do monograms on the cuffs than on actual skin. The picture really shows a few words about me. For example, I have a simplicity fetish, as indicated by that Movado watch that doesn't have any numbers on it. You know, I like to say the brightest future belongs to those who know the past the best. So no Maxwell, no physics. That's what the first 3 blogs were about. And if you know the classical field equations for gravity, that's a great place to start. So neither of those equations survive the profound message of special relativity. In both cases, the flaw is that a change in the charge density would need to propagate instantaneously everywhere in space. Not. So here is how those two equations get upgraded in order to deal with special relativity. And the top line there is known as the Einstein field equations of general relativity. And the bottom line is the Maxwell source equations written in the Lorentz gauge. So even to an untrained eye, the upgrade was minor for EM, but a complete break with the past for gravity. Now, physicists are right to beam with pride about the mathematical tour de force that the general relativity equations represent. But an untrained mind, would probably guess something, say, more like this. You know, they say, well, you know, because it worked for EM, so why not just get it to work for gravity? Now, guessing field equations like this, that's the sport of fringe physicists. What this mini-series is all about is teaching you the proper way. Drill that in, the ultra-conservative approach to field equations, which is to write down the Lagrange density first. Plug that into the Euler-Lagrange, and then pick a gauge that might just simplify the expression. And so that's exactly what I'm going to do again. Arriving at the guessed equation for gravity, not for general relativity. So the first blog in this series showed the way to derive field equations known as the Euler-Lagrange equation. The second and third blogs used a quaternion multiplication in the very first step, actually, of the writing out the Lagrange density. You know, after that, quaternions were like not used again because the Euler-Lagrange machinery took over. So here are the 4 Maxwell known equations written as quaternion expressions. And I only do that to just kind of irritate people who don't really like quaternions. But I kind of like it, you know? Oh, why do I like it? Well, you know, slimmer is better in this iPhone world. So why not for physics? Oh, note that you really don't get any new mathematical physics insight out of that exercise. I call this, quote, isomorphisms that may start a fight for 1,000, Alex, if you know what I mean. So let me just take a little quaternion sidebar since they've come up a few times. You know, since 1997, I've just had this hobby of rewriting standard equations using quaternions, you know, at quaternions.com, which I own. Yeah. And that's been a really great way to train in physics. Feynman wrote on a corner of his blackboard, "That which I cannot derive, I do not understand." Now, not that he needs my support, but I certainly agree with that position. The vast majority of quaternifications that I've done, which is a made-up word, is masturbation, resulting in the same expression up to an isomorphism. The Maxwell equations remain the same, even if I happen to write them differently with this quaternion kind of expression. I've also learned that quaternions just can't do it all. I even had a blog about that subject for the current coupling term that shows up here. It's called, I think, shot in the head, and how I had to find an alternative to quaternions. So the fundamental starting point for my work are tensors that are constrained, actually, to work in 4D spacetime. So examples would include time in 3-dimensional space, energy and 3D momentum, charge in 3 current densities, changes in time, you know, d by dt, along with changes in space. Keep them together. The scalar phi and a 3 potential A. Now those can be added, subtracted, multiplied by a scalar, and you can actually change the coordinate basis however you well please. I don't care. That's the starting thing. But there are multiple ways to multiply 4D tensors. Quaternions provide one set of rules, and those rules were used to derive the Maxwell Lagrange densities that was used in the second and third blog posts. So different rules, though, for multiplying 4D tensors are going to be the source of my variations on Maxwell equations. So I'm going to imagine a variation on a quaternion product symbolized by a box time symbol here, where I basically get rid of every single minus sign that would normally show up in a quaternion product. So let's see if we can get a nice close-up of that guy there. Okay, so we've got it goes first plus last, then outie plus innie plus what I call the symmetric cross product. So we've got the A times C and B dot D, and then a kind of two, what do they call those, scale changes, you know, when you stretch your D vector by A, stretch your B vector by a factor of C, and then that symmetric curl. Okay, what is a cross? Well, so what is that? Well, I really like it because I don't have to look at my right hand anymore. It's just like the cross product, except you don't have to remember which sign is positive or which sign is negative. They're all positive, all right? So that's great. Now, this is a reinvention of mine. It can actually go under several different aliases. It can be viewed as a form of something known as the hypercomplex numbers. Now, I'm not a big fan of that label since nothing appears to be hyper or complex about it to me. Now, most representations of hypercomplex numbers, have a minus sign or two in the products. The California representation of hypercomplex numbers, well, that has much better marketing appeal, but is actually too long. The California bit is just supposed to indicate that, no, it's all sunshine. Somebody suggested actually California numbers, but for this blog I'm going to actually shift again, talking only about California products. It's because we're going to be starting with 4D tensors that can form either the quaternion or California product, depending on what's needed. MathWalks are probably not going to be happy with my little hydra here. The California product, I mean just the product, the multiplying part, is really nothing more than the Klein four-group in action, for those of you who know about the Klein four-group. So the California product commutes. Division, though, is not assured. There will be non-zero values where it comes out to be 0. I actually do know how to determine if an inverse exists. You simply calculate the eigenvalues of the matrix representation, which I do by asking Mathematica what that is. Now, if none of those eigenvalues turns out to be 0, then an inverse exists. And I think that observation is kind of fun because eigenvalues play a key role in quantum mechanics. So it turns out that events on the light cone are actually part of those that are excluded, which is also interesting from a physics perspective. Now, the California product also is not very norm friendly. What's the size of this thing? Not going to work out. Because all that positivity means that the imaginary part, like, always hangs around. See, for the norm of complex or quaternion product, the magic happens is that all the numbers end up crowding up into the scalar part there, okay? And you've got a 3 vector that turns out to be 0. And you just can't do that for quaternions. So for hypercomplex numbers. For the California product, doesn't work out. So there's actually one more technical detail I need to clarify before we go on. And that is that the current coupling term needs to be invariant under a Lorentz transformation. And the California product doesn't have the required minus signs to make it so. So therefore you use a conjugate operator like so. And you can see that scalar, I should say that first term there is going to be invariant under a Lorentz transformation. All right. Now a conjugate operator can also be called a 3D mirror reflector because that's what it does. Or I could claim I'm working with a dual vector space. Now I actually prefer to think of this as a mirror operation because I can picture a mirror. I've used them many times. So it makes it seem kind of more physical and more real. So now we're going to construct the complete set of first order changes for a space-time potential. And to create a variation on EM, we're going to use the California product, and we're going to toss in one of those conjugate operators. And so there is what we get out of this process. So we get a gauge term, which is what that d phi dt minus del dot A. Then if you know the definition of the E field in EM, that's big E is minus dA dt minus del phi, you go, ooh, well this isn't that different, is it? It's just got one minus sign different. And then we've got that symmetric curl thing. And so I define those as being G for gauge, and the symmetric E field and the symmetric B field. Okay? So that's how I define it. Alright, so that gauge term G is actually exactly the same one as that shows up with a quaternion product EM field definitions. And that detail is actually going to be essential in the last blog of the series to deriving the unified gem equations. So exactly half the signs showing up for what I define as this symmetric small e and small b fields have flipped signs relative to their EM electric and magnetic field counterparts. That's kind of cool. Just as 90 degrees as they can be. Now, the Maxwell Lagrange density actually required two variants of those field definitions. That was accomplished by changing the order of the del and the A, and that worked because quaternions do not commute. Well, the same trick is not going to work for California products because those do commute. So what you can switch though is who gets the mirror, and that will change things a little bit. Okay, and here's me working it out. I also decided to get rid of the gauge field like I did before, because that way this thing travels at the speed of light. And okay, so I did change the order, but that's so I could say, hey, the conjugate the first one. Okay, and what's fun about this is it's the E field that flips signs, not the B field. That was a little unexpected, but that's because the B field has two signs, and it has the same sign for both terms, and the E field, one's going to be positive, one's going to be negative. So that's why that guy is flippable with a conjugate operator. Okay, so the Lagrange density, has to be written out by all of its component parts. So the symmetric small b field is easy now, because I don't have to remember which one is positive and which one is negative. It's just these two things. And I'm using this yellow highlighter in here because I want you to see which terms are changing around. This really is a variation. That's why I can use the same basic symbols, the same graphics from video to video. I just have to highlight where things change. So the small symmetric E field requires some thought. I can't actually remember why I chose to define it, the field this way, but it doesn't matter too much as long as you're consistent. So I'm flipping the sign on the A in my definition. So we square both terms, and we see that what changes is the mixed term. So now we subtract one from the other, and we see that we get very similar kind of thing as we did before. Well, actually, the current coupling term is exactly the same, and the cross terms happen to flip signs, but otherwise everybody else is there. So the current coupling term and the difference of squares need to be combined. Now, one could either take the sum or the difference of those two. And of course, the resulting laws would be very different depending on how you did that. Now, I want the equations in the static limit to give me Newton's law of gravity. And for that reason, I actually need them to be kind of a different sign in there. And so here is the Lagrange density in all its component parts. The sign flip means that the mixed terms are staying the same and all the squares flip. Okay, so now we go over a micro review of the needed calculus to deal with Euler-Lagrange. And so we focus on one term at a time, the phi one, and you basically end up kind of doubling up all kinds of derivatives, and that really is about it. So we're going to focus on the terms with a phi, the ones that are over on the right side. We've got one current coupling term and 6 derivative terms. We start taking the Euler-Lagrange and getting these second order terms, some mixed, some second order guys. And we're actually free to choose a gauge because the gauge terms were, targeted for elimination. They were subtracted away when we formed the Lagrange density. And this is known as the Lorentz gauge. And if we apply that here, we end up with this, this equation here. And this is our initial guess. But it's not a guess. No, no, no. It is part of the standard way to derive field equations starting from a Lagrange density. And so here is our summary statement. This has got Newton's law inside of it, but in a way that is compatible with special relativity. Things are not going to have to go instantaneously from here to there. We've got time derivatives, and so we can be at peace with special relativity. So now we're going to calculate the symmetric Ampere's law, which is just really darn similar. We're going to focus on the AX terms, and they're kind of spread out, one per line, as it were. And then we apply Euler-Lagrange, and we try and figure out what terms these really are. That does require some work. And here again, we try and figure out what this equation is going to mean or be in the Lorentz gauge. And the three field equations look like this, kind of wacky, but each term has two positives terms and two negative terms. Now, one nice feature of the Maxwell equations written in the Lorentz gauge is how simple they behave under a Lorentz boost. The current density is a 4-vector, the D-Lambertian is invariant, and the 4 potential transforms like a 4-vector. So simple is good. The world is not always simple. I mean, yeah, we've got the same 4 potential that's going to transform like a 4-vector. The differential, though, is not the D-Lambertian. The way that differential transforms under boost can actually be calculated in a straightforward way. Now, whether one can find a pithy way to describe, the interaction of the two of these together, well, that's a different issue. I actually don't know it. So the current density much J can't transform like a simple 4-vector. As a matter of fact, it's got to give us certain clues that it involves like spin 2 particles, because you need spin 2 particles in order to have like charges attract. So you've got to be able to spot that kind of symmetry in there. Now, I actually don't know how it transforms at this point. I mean, that's an area of study, and that's about it. Now, for those who want to see that these field equations are like consistent with current tests of weak field gravity via solutions to the equations, well, that's a legit request. I can tell you that what I've been able to do is show that the exponential or Rosen metric is in fact a solution to these both of those equations, both the kind of symmetric Gauss's law and the symmetric Ampere's law, but it's in a different block. There's only so much you can do, and what I intended to do here is just to derive these field equations. So here's my summary statement. This is my Ampere's law for gravity. And we can actually compare and contrast the hypercomplex Gauss's law with Ampere's law and kind of see this pattern developing. Now, there is no vector identity I can spot using a California product. All those positive signs means there's no nice way for things to really cancel out. This is actually good news. All right? We have extensive experience with gravitational monopoles like the Earth, Gravity, only knows how to attract. And the California product doesn't know a minus sign. So this really sounds like they were made for each other. All right, so here's my snarky puzzle. Show that b squared, small b squared, minus small e squared is invariant under Lorentz boost. And I'm pretty sure I did that calculation once, but I'm going to have to go find it. All right, thanks a lot.